Hello, welcome to this short supplement on velocity and distance in the Hubble Law for the Expansion of the Universe course. We will also introduce the cosmic distance ladder. The lecture script is available at a link given in the description of this video. In 1929, astronomer Edwin Hubble published evidence that for 18 galaxies further from us than Andromeda is, those galaxies are receding away from us, and the recession speed is roughly proportional to distance, though with considerable spread in the data. The horizontal axis in Hubble's plot is distance, the actual distance, called the proper distance, of the galaxy from us now. The vertical axis is velocity, speed, moving away from us now, recession speed. This proportionality came to be called Hubble's law, now called the Hubble-Lemaitre law. It is a linear regression trend line fitted to data with a good deal of spread. At larger distances, the law gets replaced with a different graph, but always there is spread in the data. Recession speed equals Hubble's constant times the proper distance. H sub 0 is called Hubble's constant. How did Hubble determine recession speed and distance? And how do modern astronomers? First, we look at velocity from us. This is always radial velocity, which is radial speed, but it is called velocity. In Hubble's 1929 plot, the recession velocities of galaxies, the vertical amount, were actually redshifts of starlight absorption lines from the outer layers of the stars in those galaxies. If the galaxies were moving away from us in fixed space, the redshifts would be due to Doppler shift. For distant galaxies, this gets reinterpreted as due to the cosmological redshift of the expansion of the universe, with a small component of Doppler redshift or blue shift due to galaxies, including our own Milky Way galaxy, moving relative to local space due to gravitational attraction to nearby galaxies. Physicists and astronomers know the emission and absorption light wavelengths of very many atoms and ions here in the lab very precisely. Astronomers use spectroscopy to measure detected light wavelengths very precisely. They match up detected redshifted wavelengths of absorption lines, as on the bottom image, to laboratory wavelengths, as on the top image. The astronomer divides the observed detected redshifted wavelength by the wavelength they infer was emitted, and then subtracts 1 to give the redshift value z. For small redshift, the recession velocity equals the redshift z times the speed of light, c. The vertical axis in Hubble's plot was the speed of light times z obtained from visible spectra, obtained by another astronomer, Slipher, in the 1910s. Modern astronomers still use the redshift z, but no longer turn it into a recession velocity, as that formula is not correct for z greater than 0.2, whereas z does give the expansion scale factor, as we covered in the main course. Notice that there is still considerable scatter in the data. Now we look at distance. First, we will look at how Hubble assessed distances to galaxies. Most stars have pretty constant luminosities, but some stars have variable luminosities, as discovered in the late 1700s. Some of those stars' luminosities vary periodically. In 1912, Henrietta Swan Leavitt published a period luminosity relation for the class of highly luminous supergiant stars called Cepheid variables, which she had studied in the Milky Way and the Magellanic Clouds. But at that time, the distance from us to the Cepheids in the Milky Way were not well known, so only relative distances could be determined from inferred luminosity and measured flux. In 1924, Edwin Hubble used the largest telescope in the world and found a Cepheid variable star in the Andromeda Nebula. This star was much dimmer than the Cepheids in the Milky Way and the Magellanic Clouds, so Hubble concluded that Andromeda was its own island universe, which we now call a galaxy. But since the distances from us to the Cepheids in the Milky Way were not well known at that time, Hubble's estimate of the distance to the Andromeda galaxy was not accurate. Astronomers now have better distances, but it's complicated. Astronomers use multiple techniques to develop and maintain a cosmic distance ladder to determine galactic distances near and far. No one technique works for all distances, so astronomers rely on overlap between the techniques. The first requirement is to know the distance of Earth's orbit of the Sun, which is now well known. The second rung on the distance ladder is to calculate the distance to nearby stars using stellar parallax, apparent shift of a star's location against fixed distant star background over half a period of Earth's orbit. Distances to hundreds of nearby stars could be determined from ground astronomy before the advent of satellites, but unfortunately this did not reach to the nearest Cepheid variable stars. The Hipparcos and Gaia satellites determined the stellar parallax distances to hundreds of thousands of nearby stars, including nearby Cepheid variables. This allowed more accurate calculations of distances to the Magellanic Clouds, the Andromeda Galaxy, and other nearby galaxies in which Cepheids were found. How bright a candle looks depends on its distance from us, according to the 1 over distance squared relationship. Twice as far looks 1/4 as bright. For cosmological distances in our expanding universe, distant galaxies are even dimmer than the 1 over distance squared relation. If an astronomer sees a star or supernova in another galaxy, for which the astronomer believes that they know the absolute luminosity, L, that star is a standard candle whose measured flux or brightness can be used to calculate the luminosity distance to the galaxy. Then the current proper distance, d sub p, can be calculated using the measured cosmological redshift, z. The luminosity distance is larger than the proper distance, and the distant galaxy appears dimmer than it would be if the universe were not expanding. The formula that I gave here is for a flat universe, zero curvature. The widths of galaxies also look smaller at larger distances. However, for an expanding flat universe, very distant galaxies appear wider than they would be if the universe were not expanding. If an astronomer uses some presumed standard ruler, galaxy or object, they can use the observed angular diameter to calculate an estimated distance. Here is a chart of the different techniques used in the cosmic distance ladder, also called the extragalactic distance scale. The vertical axis is distance from us. From nearby at the bottom to a few hundred megaparsecs at the top. Each bubble is only useful over some range of distances, so it is important when multiple bubbles overlap at different distances. Cepheid variables are on the right. There are also two other classes of variable stars for which period-luminosity relations have been determined and are used in the cosmic distance ladder. RR Lyrae stars are on the lower left. Accuracy is improved when astronomers find more than one Cepheid and RR Lyrae star in a galaxy. Both types of variable stars are standard candles, but they are not bright enough to use for more distant galaxies. Supernovas are very bright as a galaxy, and can be seen in more distant galaxies. A subset of supernovas called type 1a supernovas have rise times to peak brightness and fall times that are strongly correlated with their absolute luminosities. Astronomers use the rise and fall times to infer absolute luminosity, and then use the measured flux to calculate distance to the galaxy. This is the bubble at the upper right, type 1a supernova. The most distant type 1a supernova yet observed had redshift Z close to 2. The James Webb Space Telescope has detected far older and more distant galaxies than that. Astronomers use these type 1a supernova data from many distant galaxies to calculate the Hubble constant and the cosmological parameters of the expansion of the universe. Unfortunately, these results differ by about 10% from results from the cosmic microwave background, so this present Hubble crisis needs to be resolved. Gamma ray bursts are even brighter than supernova, though not as well standardized. Some of the bubbles in the cosmic distance ladder use other techniques, for example, standard populations, which help astronomers to build a consistent picture over a wide range of distances.